Okay, in this section we're going to take a look at something called the binomial theorem and how it ties into Pascal's triangle and where it's useful for some algebra and some other things. So first of all, the binomial theorem. Let me just start by taking some algebraic terms and expanding them and taking a look at some patterns. So if you have a plus b and you raise it to the power of 0, that would just equal 1. And if we just looked at the coefficients, well, the coefficient of 1 is kind of boring. It's just basically 1. If I take a plus b and raise it to the power of 1, then I end up with a plus b. And now my coefficients are a little bit more exciting. They're 1 and 1. If I take a plus b and square it, so you have to actually think about the distributive law, writing the brackets out twice, distributing and collecting like terms, you get a squared plus 2ab plus a b squared. And the coefficients go 1, 2, 1. If you take a plus b cubed, you get a cubed plus 3a squared b plus 3ab squared plus b cubed. And I'm doing a lot of the algebra for you. You can double check this if you'd like, or you can trust me on this one. I get these coefficients. And you can continue this pattern as long as you want. I'm just going to do the fourth one, so I would get a to the fourth and 4a cubed b and 6a squared b squared and 4ab cubed and ab to the fourth, and I'd have coefficients of 1, 4, 6, 4, 1. And so you can see those 1, 4, 6, 4, 1. Now, the numbers that are formed over on the right-hand side with those coefficients, the 1, and then 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, there's actually a number of neat patterns that are happening in there. And this can continue, and so can this forever. But let's take a look at this in a little bit more detail, because it has a special name. In fact, it's called Pascal's triangle. So remember we had those powers. We had power 0, and that became a 1, and then we raised it to the power of 1, and it became 1, 1, and raised to the power of 2 became 1, 2, 1, and to the power of 3 was 1, 3, 3, 1, and the power of 4 was 1, 4, 6, 4, 1. If I raise it to the power of 5, here's how I continue this pattern. Well, the first one's always a 1, and so is the last one, but these two together add up to this one. So 1 plus 3 gives me that 4. So 1 plus 4, this should be a 5. And 4 plus 6, this should be a 10, just like 3 plus 3 gave me a 6. So I should get another 10, and I should get another 5. And if I continue this pattern down, so I'll give myself a little bit more space, 1 plus 5 is 6, 15, 20, 15, 6, 1, then I would know that it would be expanded out, a plus b to the power of 6 would get expanded out with these coefficients. It would be a 1, a to the 6, and then 6, 15, 20, 15, 6, and 1. And this could be really useful for helping us expand out these binomials without actually having to calculate and take all that time to actually use the distributive law over and over and over and over and over again. But there's a whole bunch of other patterns that are happening in here. So these things here are known as rows. This is row 0, this is actually called row 1, and so these are all rows. And eventually you'll get down to an unknown row, which would be row n. Now there's another pattern in here. This is an interesting one. The sum of the row. So this one is just equal to 1, and this one is equal to 2, and this one's equal to 4. 4 plus 4, this one's 8, 10, 11, 12, 16. Oh, look, there's a pattern. Times 2, times 2, times 2, times 2, times 2, times 2, and you can keep going. And so if you look at the row number and this number, this is like 2 to the 0, and this is 2 to the 1, and this is 2 to the 2. So row n should probably be 2 to the n. That's a really nice little pattern that happens in here as well. By the way, there's lots and lots of these patterns. You're not expected to know them all, but it's just kind of interesting. There's also a few other patterns that happen, or things that you'll notice that happen with all of these. So let me just list some of them out. First of all, the rows always start and end with 1. We just noticed that the sum of each row is 2 to the n. The numbers in the rows are generated by adding the numbers that are directly above it. So if I want to know how I got this 6, well, I added the numbers that are directly above it. And the number of terms in a row. So in the first row 0, there's 1 term, and in row 1 there's 2 terms, and in row 2 there's 3 terms. So the number of terms in a row is 1 more than the power of that binomial, 1 more than n. Now, when we were taking a look at taking binomials, like up here, the a plus b is a binomial, and expanding them out, you'll also notice that there's some patterns with how the letters and the powers with the letters go. So there was an a, and then there were no a's. There was a squared, then a to the 1, then none. A cubed, a squared, a to the 1. A4, a3, a2, a1. And so you'll notice that they start with the a's being the same power as the power that it's raised to, and then it decreases by 1. For the b's, you get no b's, and then a b to the 1. No b's, b to the 1, b squared. No b's, b to the 1, b squared, b cubed. B to the 0, b to the 1, b to the 2, b to the 3, b to the 4. So where the first variable is starting at its highest power and decreasing, the second variable starts at power 0 and increases by 1. So we see that pattern where x is decreasing, the first variable is decreasing from x to the n to x to the 0, and the y is increasing from y to the 0 to y to the n. And that actually makes expanding out binomials really easy to combine both of these things together. So let's see if we can do that. If we expand x plus y to the n, well, there's a few parts. We need to know those coefficients, and then we need, well, x will be to the n, and in the next term we'll need a coefficient, and y will be to the 0. We'll have x to the n minus 1, but y will increase by 1. And then in the next term we've got a coefficient, and that'll keep going until we get to the last term. A coefficient, and then x to the n minus 2, y to the 2, and that'll keep going until we get to the very last term, and there'll be a coefficient for the last term, and then x will be to the 0, and y will be to the power of n. So y0, y1, y2, all the way up to yn, xn, down by 1, all the way to 0. Now the coefficients, we know the first and the last one have to be 1s. How do we find the other ones? Well, actually, there's even a cooler secret, and that's that they're based on combinatorics. In fact, they're based on combinations. So this first one will be n choose 0. So however many objects you have, if you don't choose any, there's only one way not to choose any. So that'll always be equal to 1. And the last term is, what if you had n objects and you took them all? Well, there's only one way to take all the objects, so that's also equal to 1. And then in between, you've just increased by 1 and increased by 1 and increased by 1 as you go along until you get to n. So it's a pretty neat little thing that Pascal's triangle actually has to do with combinatorics as well. We'll take a look at that a little deeper in just a couple of minutes. First of all, I want to try a couple of examples, or at least one example here. What if I have x plus y to the 6th? What does the expansion look like? Well, the coefficients, I do them first, so I'm just going to do all the coefficients. I'll do them in blue. I have 6 choose 0, then I'll have 6 choose 1, then I'll have 6 choose 2, then I'll have 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. And then I'll do the x's. I'll have x6, x5, x4, all the way down to x0. I don't write the 1 and the 0 in, and then in green I'll do the y. So I start with y to the 0, then I have y1, I don't really need the 1, y squared all the way up to y to the 6th. And then all I need to do to get my answer is just do some simplification. So my calculator will tell me the first, well, I know the first one's a 1, and then these are just all added together, all these terms. And so my next one is 6x5y. And then I can either create Pascal's triangle, or I can use my calculator to get 6 choose 2, which is 15, and that'll be x4y squared, and 6 choose 3 is 20, x cubed y cubed. And remember we talked about how there's some symmetry to this, that taking 6 objects and choosing 2 is really the same as taking 6 objects and choosing 4. That's why there's symmetry where the numbers go back to, okay, well, there's 15 ways of doing x squared y to the 4, there's 15 of those, and then so the next number is going to be 6, x, y, 5, and back to one way of choosing y to 6. That, I hope you can see, is a lot faster than taking x plus 6 times x plus 6 times x plus 6 times, x plus y 6 times, and expanding all those different brackets out using distributive laws collecting like terms. This is a much, much, much faster, more elegant approach to those expansions. Of course, there are times when we just want a specific term, like we just maybe want to know what is this term, 1, 2, 3, what is this fourth term of the expansion of x plus y to the power of 6. And we really don't want to have to calculate all the terms, especially if I want to know the fourth term of x plus y to the 60th. I really don't even want to, I know there's a shortcut for getting all 61 terms of that, or all 7 terms of this, but I don't really want to have to go through all that work if there's a shortcut to just get a specific term, and there is. And it looks like this. And this is a really useful formula. It's that term, and we'll call it k plus 1. So in this case, if I want term 4, then k plus 1 is 4, so k is 3. And that's the trickiest part with this. So the fourth term, where k is actually 3, is equal to n choose k times whatever the x variable is to the n minus k times y to the k. So again, if I've got the fourth term of x plus y to the 6th, and I understand that t of 4, essentially I want t4, so k is equal to 3, then I should just be able to take, well, the n for this is 6, choose, and the k was 3, and you'll see that's exactly what I had calculated. This is where it's coming from. 6 choose 3. Then the x value will be raised to the 6 minus 3 power, which is 3, and the y value will be raised to the 3 power. And just by that example, you can see that I did get it right with this one. So this formula works, and it's way faster than having to calculate them all out. So let's try one example with this. And I'm going to throw one other little quirk in there, which is it doesn't have to just be x plus y. It can be something plus or minus something else. So you think about this part as your x, and you think about this part as your y, including the negative sign. So let's try this one. I want to calculate t10. So t10 means that 10 is k plus 1, or k is just 9. That's the tricky part. Then the 10th term of this one, so here's n is 15, and we're doing 10th term, k is 9, so I get 15 choose 9, so 15 choose 9. My x is really 2x. It's to the power of n minus k, 15 minus 9. And then the y, which is really negative 11, is to the power of 9. Now this is going to turn out to be some really big numbers here. 15 choose 9 is 5005. And then I've got 2x to the power of 6 and negative 11 to the power of 9 still to worry about. So this is times 2 to the 6 times x to the 6th, and still times negative 11 to the power of 9. Give myself a little bit more room here. 2 to the 6 is 64, and negative 11 to the power of 9 is negative 235,794. It's a huge number, 7691, and then simplifying all of this out gives me this massive number. And there's no way I would have wanted to expand this thing out just to calculate that 10th term. It would have taken forever to calculate all the 9 terms before it. So this is still a difficult procedure, but a whole lot faster than expanding these things out by hand or even with the binomial theorem.